Hey everybody, we're going to spend a little bit of time in this video talking about acid-base theories and what makes an acid and what makes a base a base. So there are probably 2 or 3 very common acid and base definitions. And I know that sounds strange. It sounds like, it should be that there should just be one definition of an acid and one definition of a base. But that's not entirely true. We'll talk about the most common definition of a acid and a base, and that's the Bronsted-Lowry definition right here. Okay, and so the Bronsted-Lowry definition of an acid and a base is that an acid is something that when it is in solution will donate a proton, and a base is something that will accept it. Now, there are 2 other common definitions of acids and bases. One is Arrhenius, named after Svante Arrhenius. Okay, and an Arrhenius theory is based solely on structure, where you have an ionizable hydrogen on the acid, so something like HCl or HC2H3O2. Okay, this is acetic acid or maybe vinegar. This is hydrochloric acid or muriatic acid as a common name. And so this hydrogen out front indicates that it's an Arrhenius acid. Okay, bases using Arrhenius theory are indicated by having hydroxide ions at the end. So things like NaOH, that would be considered an Arrhenius base. Okay. Now, unfortunately, Arrhenius realized that this definition doesn't really encompass every compound. Acids, okay, but what if you have a compound like NH3? They knew that NH3 was that acted as a base, but if you see, there's nowhere where it has a hydroxide ion. So in comes Bronsted and Lowry, and when Bronsted and Lowry came in, they decided, instead of talking about hydrogen ions and hydroxide ions, they were really only going to talk about the flow of hydrogen ions. Okay, and just a quick thing and the reason why I'm bringing this up is because it took me until my first year of graduate school to figure this out. Everybody always talking about proton donors, and I've talked about protons and hydrogen ions and all this good stuff. A proton is an H+. Okay, think about it. A hydrogen ion has 1 proton, and that's it. Okay, the 1 electron has been lost. So when we're talking about proton donor, we're going to use that interchangeably with the hydrogen ion. Now, there is a third theory of acids and bases that's pretty common, called the Lewis theory. Yep, I will tell you that it's that Lewis, Gilbert Newton Lewis, the guy who came up with Lewis structures. He actually determined, figured out Lewis structures because of his research with acids and bases. But we won't talk about Lewis acids and bases in great detail. Okay, but the Bronsted-Lowry theory of acids and bases is kind of where we're going to go, what we're going to use to define our acids and bases. So here we have kind of what happens when a Bronsted-Lowry acid reacts with water. Okay, so here we have HCl, and I'm going to get pretty specific here. Okay, this is hydrochloric acid. Actually, let me just say that this is hydrogen chloride. Hydrogen chloride, when it's mixed with water, actually ionizes. And so what happens is this hydrogen is transferred. So based on our definitions of acids and bases, this hydrogen donates the proton, or sorry, this compound donates the proton, it's an acid, and water here, H2O, accepts it. So that makes this the base. Okay? And so it's not until this happens that HCl is considered an acid. Okay? So HCl gas is hydrogen chloride. HCl gas is hydrogen chloride, not an acid. Okay? But then HCl aqueous is an acid. Okay? And I think that is important because Bronsted-Lowry acids and bases are always talking about where the protons are going. So it's not until the proton moves around that something actually becomes the acid. And it's this thing here, this thing which if we write the formula of is H3O plus, it's this molecule or this ion that actually is responsible for the change in the acidity or the pH. Okay, and this ion, that has a name, and you'll hear me call it the hydronium ion. Okay, that hydronium ion is the thing that causes something to have pH. Okay. Now, this slide is a little deceiving because it says you will recall. I'm not sure exactly what you learned in your previous chem class, but there are 7 strong acids: HCl, HBr, HI. Let me say it a little bit differently: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. Those are all strong. Okay. Now, I wish I had a way for you to memorize to know these other than just say you have to memorize them. I'm not a big fan of making you memorize things, but unfortunately in this case you just have to know the 7 strong acids. Now, a strong acid is strong because this compound completely ionizes. When HCl mixes with water, okay, now watch what I'm going to do. I'm going to draw that arrow. This forms H3O plus, the hydronium ion, plus Cl. It's not in equilibrium, okay? And so that makes this a strong electrolyte, or a strong something that is completely soluble. And so these strong acids, what happens is if we know the concentration of the acid, we know what the concentration of the hydronium ion is. And remember, the hydronium ion concentration is related to the pH. Okay? Now, just like there's strong acids, there are strong bases. And I wish that I had a way for you to know these. I guess there is a little bit of a pattern. They're all the alkali metals, like lithium and potassium and on down rubidium. You can go down the line. And some of the heavier alkaline earth metals like calcium, strontium, and barium. Okay, all of those hydroxides are strong bases. There's 8 of them if you count them all up. Okay, now what does that mean that they're strong? It means they completely dissociate. Okay, so that means when lithium hydroxide is in water, you end up with Li plus lithium ion plus hydroxide ion. Now, a base reaction is a little bit different because in this case we don't have H plus, or we don't have H3O plus, so there's a little chemistry that goes on here. Okay, and so that's the list of strong acids and strong bases, and you kind of need to know which is which. And now we're going to talk about one last thing, and that's what happens with water. And so lastly, I want to talk about this slide here, and it would be super strange if water was considered a strong acid or a strong base. But water, as we know, in a lot of ways is special. Why is water special? Because it does something that we call auto-ionizes. Okay, water, if we use the Arrhenius theory, we can see water has an H out front. But let me show you a little trick here. We can rewrite water, try to say that 3 times fast, as HOH. So again, using Arrhenius theory, look, we have an H out front, but we have a hydroxide also out back. And so by Arrhenius theory, this is an acid and a base. And that's true. It's an Arrhenius acid, and it's also a Bronsted acid and a Bronsted base. Okay, well, what makes it that? It's because when water is in proximity with another water, what happens is it ionizes. And notice here in this case, and this is kind of a portent of things to come, notice that we have an equilibrium arrow here. So this is not strong. That would be totally weird if water was strong, completely ionized. But what we have is we have the formation of the hydronium ion, the thing that gives us the pH, and the hydroxide ion. And those are equilibrium. There's an equilibrium between the hydrogen ion and the hydronium ion and the hydroxide ion with the starting material. Okay, so make sure you know your 7 strong acids and your 8 strong bases, and realize that there's lots of definitions of acids and bases, and water can act as both an acid or a base. So have fun and have a great day.